Okay, this is going to be our fifth and final video in our electric potential series. And in this video, we're going to be talking about potential gradient. So this is all the material from section 23.5 from the text, and we'll get right into it here. We have a few new concepts we're going to have to introduce, but we'll get to them as we go. Okay, so we've seen how the electric field and our potential function, our V, relate through the equation that we see here, through equation 1. Okay, and we've seen how if we're given the electric field, we can use this expression to get V, right? Now we want to see if we can kind of turn this problem on its head. We want to see if we can get E from V. Okay, and so let's say we're given some V as a function of position, so we're given some V as a function of x, y, and z, or as a function of r or something, right? As a function of some sort of position. We can find E, our electric field, our vector E, by taking partial derivatives of V. So we're going to talk about partial derivatives in a second, but let's first set it up. So we start off with our with this expression that we have here in equation 2, and I had some typos, so I fixed those up. But what we have here is our potential at A minus our potential at B. So VA minus VB is the potential of A with respect to B, and this is the change in potential as we move from B to A. Okay, so we can write this down as we normally do up here, right? Or we can write it down in this way as we have down here. Okay, so we can write it down as a difference. VA minus VB is equal to the integral from B to A of dV, where dV is an infinitesimal change in the potential on the path from B to A. Okay, and in the second equal here, in this second equivalency, I'm just flipping the sign on the integral. And I want these limits of integration to be this way so that I can equate it to the equation that we have above. Okay, so I flip the limits of integration, pick up a minus sign for doing that, and now I can equate this through this with this and this, right? So what do we end up with? We end up with minus the integral from A to B of dV is equal to the integral from A to B of E dot dl, right? And because we have the same limits of integration here, this means that our integrands have to be equal. So we can drop the integrals, and really what we end up with is minus dV is equal to E dot dl. Okay? And what we're going to want to do now is we're going to want to write these vectors, E and dl, in terms of their components. Okay, so we can break them up. We know we can write E in terms of its coordinates x, y, and z, as is written here. So E is going to be equal to its x component in the I hat direction, its y component in the j hat direction, and the z component in the k hat direction. And the same idea is true for dl. We're going to have infinitesimal little chunks of displacement here, dx, dy, and dz in the I hat, j hat, and k hat directions. Okay, so if we do the dot product between the two of these as equation 3 here would suggest we need to, we can clean things up, and we end up with the expression that we see here. We have minus dV is equal to the x component of our electric field times dx, the y component dy, and the z component dz. Okay? And now is when we need the partial derivative. So I have a tiny little aside here for partial derivatives. Some of you may have seen these before, some of you haven't. It's really not a big deal. This is not like some hugely new concept. A partial derivative is basically just a normal derivative where we're reminding ourselves that we're only taking the derivative with respect to one of the variables, and there may be other variables in the equation that are variable, that can change, but we're only taking it with respect to the one variable that we're interested in, right? So here's an example. Well, maybe first I should say, so normally for a regular derivative we write d by dx like this, right? When we're talking about partial derivatives, we usually write things like this, and this, people will say this in different ways. This symbol is just a d by dx like this. So some people will still call these d by dx, other people will say partial they'll call this symbol a partial, or they'll call this a del. Whatever you call it doesn't really matter, as long as you kind of write it something like this, so we can all understand what you're writing. And basically, if we want to take partial derivatives of a function, this is how we do it. So we have it in this really simple example down here. So let's say we have some function f, and it's written in terms of x, y, and z, and it's this simple function here, x times y squared times z to the third. If we wanted to take the partial derivative of x with the partial derivative of f with respect to x, so del f del x, or the partial of f with respect to x is the way we would say that, we're going to end up with, well, we're just taking the derivative of this thing with respect to x, so our x is eliminated in the differentiation, and we're left with a y squared times z to the third, right? Let's say we wanted to take partial f, partial y. Well, we would just take the derivative with respect to y. That brings down our 2, and we're just left with a y left over, so we have x, 2y, z to the third, right? And in the final example here, let's say we wanted to take the partial of f with respect to z. We would simply still keep our x and our y the same as they were, and now we're taking the derivative with respect to z, so we end up taking down the 3. We end up with a z to the power of 2 here. Okay, so that's basically partial differentiation in a nutshell. Okay, so with that tool, let's return to equation 5 here. Let's remember this equation. So we have minus dV is equal to the components of the electric field times their infinitesimal displacements. Okay. Okay, so I'm just going to scroll down here so we have most of this on the page. And so now let's say that we're interested in picking off only the displacement in our x-axis. So let's say we're looking at our electric field, and we're only interested in what's going on in the x direction, in the direction of the x-axis, right? So we can usually set dy and dz to 0 there. So we're not moving things in the x and y direction. We're only looking at what happens as we move in the x direction. Okay. In this case, we can see that minus dV is going to be equal to our x component of the electric field times dx, right? So this is just going back up to here and setting dy and dz to 0. Okay. So if we do that, we see we end up with this little expression that we have here. And we can rearrange this. So let's rearrange this. I'm going to move this dx over to this side. And if we do that, we end up with the expression that we see here, right? And we have to keep in mind again, and it's not like it would be hard to keep in mind because we have this x in the basement, but we do need to keep in mind that we still do have y and z, which can vary, but we're not taking derivatives with respect to y and z right now. Another way to write this, which kind of makes this reminder that we're not taking derivatives of y or z more sort of clear, is to write it in this way. So we could write that the x component of our electric field is equal to minus the partial derivative of v with respect to x. Okay. And so if we write it this way, we could go through and we could do this for each component of the field. Okay, so we could do this for our x component as we just did. And I like the way the textbook kind of wrote this out with these little lines going to things. So I pulled this directly out of the text. And so we have our x component, we have our y component, which is again just our function v, where we take a partial derivative with respect to y of our potential function v, and the same idea for z. Okay, so we have our 3 different components. Now we can go back and we can plop these things into our expression for our electric field, right? If we remember, we have our electric field here written in terms of components, and we can just write our electric field down in terms of these components, right? So this normally would be, well, this would normally be our electric field is equal to the negative of, and these would be components I hat times EX, but we now have our EX written like this, and the minus sign just came out here, right? So now going component by component, we can write our electric field in the form that we see here. Okay, so that's great. We can also write this in a more concise way if we introduce what's called the gradient operator. So the gradient operator is basically this operator that we see here. So take a second to sort of look at it. The symbol that we use here is, well, this upside down triangle is what's called a nabla, I believe it's a Hebrew symbol, and the symbol on top of it is just a vector symbol. When you combine the two together, we often call this a gradient operator, or grad. And so if we want to write it out in full for this coordinate system, we end up with grad is equal to, or the gradient operator is equal to I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z. So this is an operator, and it needs to operate on something to really become more concrete for us to be able to look at here. So let's say we have some function, okay, and this could be a function that's defined in terms of x, y, and z or something, right? And so let's say we take the gradient of this function. So we have our grad f here, and this is our gradient. This is going to hit our f. Okay, so what happens? This operator just goes through and hits f with each of its terms. So you can see before here we have no f's, and afterward our f has been distributed over all these terms, and we're just hitting each of these f's with each of these partial derivative operators, right? And so what do we end up with? Well, we end up with the expression that we see here, which looks very much like the expression that we see here. And so using this gradient operator, we can rewrite our electric field in terms of our potential function as we see here. So our electric field is equal to the negative of the gradient of our potential function. Okay, so that's the way you would read that. The gradient of V, or I should maybe, okay, so let me just, I think I boxed off all the ones that are important, but yeah, okay, so I'll double check after, and again, a formula sheet will be coming up here shortly. So let's remember this equation. This is an important equation, and it's also going to be important to remember what the gradient is. So maybe I will box that off. And these two equations, 8 and 10 together, give us really what we need when we're thinking about the electric field in terms of V. Okay. So the gradient of V, i.e. this expression that we have here, at every location is going to point in the direction in which V increases. Okay, so it's always going to point in the direction of increasing V, and that's just something to keep in mind, that when we're thinking about this problem sort of diagrammatically, we should think about our grad V pointing in the direction of increasing V. We also want to note that this expression for E does not depend on our choice of 0 for V. Okay, so we could choose V 0 anywhere, and it just really changes all the values of our V everywhere. Okay, so the whole scalar field just jumps up or down in value depending on where we place our 0. And so the gradient still points in the same direction because all the points have been shifted, right? So it's totally independent of our choice of 0 for V. Okay. And the final note I want to make about this whole gradient situation here, and this relationship between E and V, at least the final new point that I want to make, is that if the electric field is described only in terms of radial components, like if our electric field is written as ER in the R hat direction, right, and we're not dealing with X, Y, and Z coordinates, but we're dealing with a radial component to our coordinates, the equation simplifies to what we see here. So our ER can be written as negative partial derivative of V with respect to R. Okay, it's basically just picking off one of these terms in the gradient, or if we look further up, it's basically just taking like the one component, because we only need one to describe it here. This is a very simplified case, right, and it's all that we're going to work with for now. Obviously things could get much worse. This is the case where our electric field is only dependent on changes in the radial component R, right? If there was some angular dependence, you can imagine a sort of 3D setup where you have a couple of angles describing where you're pointing, and you also have your radial component telling you how far you are from the origin. Well, this expression could get much worse, but for us, for now, this is all that we need. So let's remember this. If we're dealing with an electric field that has radial dependence, if it's written in terms of a radial component, we can get our electric field from our V, from our potential function, written this way. Okay. Okay, so we're going to do a couple of examples, but before we do, let me just take a couple of seconds to kind of summarize a lot of what we've done here. So we've looked at several ways that our electric field and our potential function relate to one another. Okay, so we've seen also how we can calculate each of these from charge distributions on their own. In chapter 21, like our first module, or chapter 22, our second module, we looked at Coulomb's law, we looked at Gauss's law, and we found how we can calculate E from charge distributions, right? We also saw in the beginning of this chapter how we can calculate V from charge distributions, right? So we've seen how we can calculate E and V both from charge distributions if that's all we have. We've also seen how we can relate E to V and V to E, right? So we can go back and forth between the two of them. If we want to get V from E, we have to integrate. If we want to get E from V, as we just talked about now, we have to do some differentiation. Okay, we have to take some partial derivatives, right? Using our gradient function and so forth, right? So depending on what the problem sort of gives us, we can choose a sort of plan of attack, right? If it's easier for us to get V or it's easier for us to get E, we can choose whichever one we want and then translate between the two potentially, right? So there's many different ways we can come at some of these problems. For now, though, I'm just going to focus on two problems where we're looking at this getting E from V problem, and they come straight from the text here. So let's get to work on these now. Here, I have my notes here. So let me see. I think this should work. Okay. So the first problem. We have the potential at a radius r from a point charge, and we know that that's given by the expression that we see here, right? We've seen this before, and we want to find the electric field everywhere. Okay, so the easiest way to do this, I mean, let's draw the problem here. So we have some point charge Q here. And we know that there's going to be some electric field. We need to calculate what that electric field is. I mean, we know that the electric field is going to be pointing like this, like this, right? So we can see right away that this is going to lend itself very well to a sort of radial look at the problem, right? We know that everything is going to depend on the radius away from the point charge that we are. We have that symmetry in the problem. Now we could do this in terms of x, y, and z components, and maybe I'll do that in one of our meetings, or maybe I'll do it now. I guess we'll see. But let's start off by doing it radially. Okay, so we know that we can write the radial component just from the equation that we have directly above here, the equation 11. We can write the radial component of our electric field in terms of our potential function. Oops, and there should be a minus sign in here. dV dr. Okay. And so what does this mean? Well, we can just right away rewrite this. We're gonna do d by dr of the function that we have above. So it'll be q 4 pi epsilon naught r. Okay, and so I mean we can kind of clean this up a bunch, but we can see right away that we're going to pick up an additional minus sign from the differentiation. Right, this is r to the power minus 1, so we're going to end up with a minus r to the minus 2. Those minus signs are going to cancel, and so how does this clean up? Well, we end up with a 1 over 4 pi epsilon naught q over r squared. Okay, so that's our electric field outside of a point charge. Well, we obviously know this already, but it's nice to see that we can get it using the techniques that we just talked about, right? We could also do this sort of in different coordinates, right? Let's say we didn't realize or didn't want to use the radial component of this, and maybe before I move on to that, I should write that we can write our electric field here as a vector, because we know that this is all just going to point in the r hat direction, so we can easily write it like this, right? We can write it in vector form that our electric field looks like this. Okay, so this would be the scalar component of our r hat electric field right here, and then here this is the full vector expression. But let's say we didn't realize that there was this symmetry, or if we wanted to do this in x, y, and z coordinates, could we do this, right? Well, we could for sure. So we could go through and we could try to find each and every partial derivative, right? So we would start off. We'd have to write something like this. We would have to say, well, okay, so our distance r from the, and maybe I'll split this off. They do this in the text. If you want to see a more detailed view, I'm just going to kind of go through this sort of quickly to show you guys that it is possible. But basically, what you would need to do is you would need to say, well, okay, how do I write r, this distance r, in terms of x, y, and z components? Because we're in 3 space here, right? So how are we going to do this? It's going to have to be x squared plus y squared plus z squared, all square rooted, right? And that's going to be our r component. And now we have to go through and take the partials of each of these, because we need to build up this full expression here, right? We need to build up this full expression, 23.20, okay? So we need the partial of v with respect to x, the partial of v with respect to y, and the partial of v with respect to z, okay? And I won't go through the full detail, but we're going to end up finding that if we do this, well, we know we're going to have to write it like this. So we're going to be taking the partial of this, and it's going to be q, and now I'm going to rewrite r in terms of all of these these variables x, y, and z. X squared plus y squared plus z squared. So if you go through and you do this derivative, I won't do it explicitly here, but you get the idea. You're going to end up finding 4 pi epsilon naught, and you're going to have a qx on top, and in the bottom you're going to have x squared plus y squared plus z squared to the 3 over 2. And you can clean this up by substituting back in for r, right? So if you do that, you're going to end up finding that this is negative qx over 4 pi epsilon naught r to the 3rd, okay? And so that's fine. That's our x component. We need to do the same thing for the y and the z components. So let's say we did that. As the book does, I'm going to skip some steps here, and basically we're just going to end up writing down the other 2 results. So let's say we had our dv by dy. That's going to end up giving us the same thing, except now we're going to have a y in the upstairs. So we're going to end up with minus qy 4 pi epsilon naught r to the 3rd. And for z, we're going to end up with dv by dz is equal to minus q, oops, that should be a q, z 4 pi epsilon naught r to the 3rd, okay? And so we could collect all these up and put them into our expression for the electric field, right? So we would end up with, and this is just substituting back into that equation 23.20, we would end up with minus I hat, and now I would just copy in this negative, or here I guess I can do it, q x 4 pi epsilon naught r to the 3rd, and then we're going to end up with a plus j hat minus q y 4 pi epsilon naught r to the 3rd plus k hat minus q z 4 pi epsilon naught r to the 3rd, right? And we can further clean this up. We can pull out these minus signs. We can pull out a bunch of these factors. And what do we find? We're going to end up finding that this is equal to 1 over 4 pi epsilon naught. We're going to have a q up top, and we're going to end up with let's pull out we'll pull out an r squared in the bottom, so that we still have an r inside. And then we're going to end up with x I hat plus y j hat plus z k hat over r. And then we can realize that what is this x I hat y j hat z k hat? Well, this is just our unit vector r, right? If we're dividing by r, this is going to give us the vector r, and the vector r divided by r is going to give us a unit vector r. So all this together is just going to give us a unit vector r, right? Because pointing in x in the I hat direction, y in the j hat direction, z in the k hat direction, that's just pointing in the r vector direction, okay? And so if we clean all that up, what do we end up with? We end up with 1 over 4 pi epsilon naught q over r squared in the r hat direction. That's our electric field, and it should be the same as, yeah, that expression that we have up here, right? So same result. just a lot easier if we realize that we have this spherical symmetry, and so we only need to worry about the radial component. If we don't realize that, we have to go through all this, and obviously it would be a little bit longer than this because you'd have extra steps in actually doing the calculation that I kind of skipped over here, right? Well, let's move on now to the final example of this chapter. This is going to be example 23.14 from the textbook. This is a charged ring, so we're looking at the potential in the field of a charged ring, of a ring charge. And so we know that for a ring, for a charged ring with a radius a and a total charge q, the potential at some point P on the ring's axis of symmetry, a distance of x from the center, is given by the expression that we see here. So this is the same picture that we've seen so many times before, right? So we have some ring. This is the ring's center. It has a radius of a. We're looking at the electric field at some point P, and this is a distance x out from the center, right? And we've only really talked about how to calculate along this axis, right? So we already saw, well, we haven't written down here, but we've already seen what this potential function looks like. Can we get back to our expression for the electric field at that point? Okay, so we don't. The first thing to realize here is that we only have x dependence in our potential, right? We're not doing the full problem here. We can't answer questions about what the electric field is out here at point Q because we only know what the potential function along this axis is, right? And that only depends on x. And since this only depends on x, we're only looking for the x component of our electric field. So we're only looking for Ex. And because of that, we don't need to do the full gradient problem. We only need the one part of the gradient that points in the Ex direction, and that is this component here, right? Okay, and so really all we need to do is just take the negative d by dx of the expression we have above, and if we do that derivative, I won't do it explicitly here, but if you do that derivative, you're going to end up finding that you have this expression here. You're going to find that you end up with 1 over 4 pi epsilon naught, and cleaning this stuff up over here, you're going to find q x squared plus a squared to the 3 over 2. Okay, and so that would be the expression for the electric field in the x direction. That should be a 2 at this point P, some distance x on that axis, right? And so that really cleans up nicely here. We've kind of brought together a number of ideas from all three of the chapters that we've looked at here, and now we have a way to relate them all to each other and a number of tools to solve problems of this kind. Okay, I'll leave it here, and I'll see you guys in the next module.